Dobry wieczór, Szanowni Państwo. Witam też tych z Państwa, którzy obserwują nas zdalnie. Jest to wykład w języku angielskim, w związku z czym to będą już moje ostatnie słowa w naszym ojczystym języku polskim. Good evening, everyone. Welcome to another fantastic meeting of the Copernicus Festival. This evening's guest is Professor David Grinspoon of the Planetary Science Institute, astrobiologist, and we will hear about planetary intelligence. I invite all of you to think about questions that you would like to ask our speaker today, because there will be chance to do so by the end of this section. So without further ado, Professor, welcome.
Thank you. Thank you very much. It's such a pleasure to be here. I've been really enjoying the Copernicus Festival for the last couple of days. The talks and the discussions have been fantastic. And I want to briefly apologize for the fact that I don't speak Polish. I would love it if I did. You know, we Americans, when we're kids, we don't get exposed to multiple languages, and so that part of our brain kind of withers and dies. It's definitely a problem we have, so sorry about that, and I appreciate your listening to me speak in English. So the talk I'm going to give tonight is related to the research I do on planetary exploration and astrobiology, but it's a little bit of a maybe a quirky side topic of that, partially inspired by the fact that one of my favorite writers of all time is the great Polish science fiction writer Stanislaw Lem, and his perhaps most famous story, and the first one that I learned about when I was a teenager just getting into science fiction, was the book Solaris, which I'm sure many of you know, but is a science fiction story about a planet with life that's hard to understand, and then it turns out that the planet itself is intelligent, or really the ocean of the planet is intelligent. So really just a different kind of life, and I always found that really interesting. And in fact, the idea of a sort of planet-wide intelligence is one that has been explored in science fiction and also in some nonfiction literature. This is Solaris, the novel I mentioned, and H.G. Wells a long time ago wrote a book about the possibility of a world brain, and many people have noted the analogy between the internet and the possibility of some kind of planetary intelligence. So the idea is out there, and I'll return to that, but I want to tell you now how I came to thinking about this through my study of comparative planetology and astrobiology. So we live, of course, in this well, you know, the best of times, the worst of times, right? But one of the ways in which it's a wonderful time to be alive is the fact that we are exploring the planets for the first time. And this is really, we are now sort of the second generation of humans who know the planets as this family of worlds rather than just as dots moving in the sky. And of course, going back to Copernicus, our man of the festival, who was the one who first alerted us to the fact that those dots moving in the sky were planets like the Earth, and indeed that the Earth was one of that category of objects. Now fast forward all these hundreds of years, and we're actually sending spacecraft to those planets, sort of following through on what Copernicus made possible. And this allows us to see the planets not just as individual objects, but as a class of objects, as a family of worlds, and we can learn a lot by seeing them in comparison to one another, and that's what we mean by comparative planetology. And of course, now it's not just the planets in our own solar system, but the other amazing revolution more recently of our times is what you might call the exoplanet revolution, the fact that we've discovered that there are planets around virtually every star in the sky. When you look up at night in a starry sky, just about every star you see has a family of planets around it. We didn't know that 30 years ago. We suspected it, but now we have the ability to directly observe that that's true. And that's revolutionary for our ideas about comparative planetology. Suddenly, instead of the 8 or 9 or however you want to count planets of our solar system, there are literally billions of planets out there, and many thousands that we've discovered. We're discovering more all the time. And so we have this great richness, demographic richness of planets within which to try to put our own solar system and our own planet in context. Now, astrobiology is, simply put, the study of the possibility of life elsewhere in the universe. So what do astrobiologists study since we haven't found any extraterrestrial life yet? We study the life on Earth, looking for patterns that might be universal, that we hope to learn something about the possible universals of life and the limits of life. And we study other environments in the universe, other planets, to try to understand where these limits of life, those conditions might be met elsewhere, where we might find extraterrestrial life and how we might go about locating it. Another way to think about what astrobiology is trying to do is locate ourselves within the story of cosmic evolution. When I say cosmic evolution, I mean sort of the whole story of the universe, 13-point-some billion-year-old story. But when we think in terms of cosmic evolution, we think of sort of the major chapters of that story, the major transitions that the universe has gone through from the Big Bang to us and beyond. And we can look at it like this. This is my one-page cartoon history of the entire universe. This is the story of cosmic evolution. And, a lot of the details are left out because I'm compressing 13 billion years onto one page. But some of the major plot points are here. Of course, starting with the Big Bang, which you've heard about, and I won't belabor here. But then the first structures were galaxies and clusters of galaxies, the giant clumps of matter. And within galaxies, we had molecular clouds, giant clouds in space, which spinning and collapsing formed stars, which you see down here on the bottom left. Moving up to the top right there, around forming stars, we also had planet formation. And on at least one planet that we know of, the origin of life. Some interesting chemistry early on in the history of that one planet led to some self-perpetuating chemical reactions that we call life. And then various things happened, and down there you can see on the lower right we have what we call the evolution of complex life and what has been called civilization. We can question whether that's an apt title for some of what we have, but I think we at least know what we mean when we use that word. And then, of course, it ends with question marks. What's next? Because there's no reason to think that whatever stage we're at now is the end or the apotheosis of the story. So in a sense, what astrobiology is trying to do is to place us within that story and to answer the question, how universal is this story? Now, interestingly, everything on the left side of that slide we know is universal. That is, with our space telescopes and our spectrometers and our other instruments, we know that throughout the whole universe there's been galaxy formation and star formation. Oh, and by the way, inside those magnifying glasses, you can see that's what's happening on the micro scale. So here you have inside of stars, you're having the first elements stars are element factories where nuclear fusion is burning hydrogen into helium, into carbon, nitrogen, making all the elements. And then around forming stars, you have some simple organic molecules, and then on the surfaces of planets, you have more complex organic molecules which allow the origin of life. But everything on the left side we know to be universal. Everything on the right side, we've speculated as to whether these things are just local or universal. Except, by the way, in the last 30 years, we discovered that planets are universal. They're everywhere. And thinking about life And even intelligence in that context is everything. Is interesting. It's also everything. But it's interesting because if I had been giving this lecture 30 years ago, I would have said, everything on the right side here is speculative. We don't know if there are other planets. We think there are other planets because everything we know about our sun is normal, therefore there should be other planets. But we're still trying to find them. That's what I would have said 30 years ago. Now I'm saying that same thing about life. We've found planets, and when I talk about life, I say what we said about planets 30 years ago. Well, everything we know about life seems to suggest that our planet is normal and the conditions ought to be right, so we think there's probably life elsewhere, but we haven't found it yet. So we're trying to do, in a sense, with life and even with complex life, what we have been able to do with planets, which is move it from just this speculation that it ought to be there and find out if it really is there. And that's really, in a large sense, what astrobiology is trying to do. Now, on the bottom here, of course, speaking of civilization, we are in an interesting phase on our particular planet, where the planet is being changed rapidly by this one species, and we're trying to get a handle on that for many reasons, including just survival. We better get a handle on it and understand our role on this planet better if we want to be here in the future for as long as we've been here in the past. I mean, human civilization is, roughly speaking, 10, 15,000 years old. If we want to survive that long again, we better learn how to manage ourselves on this planet a little bit better. And so there's a lot of thought going into how do we characterize, from a planetological point of view, this phase that we're in, where one species is changing the planet rapidly. And this has been called the Anthropocene epoch. In other words, the idea is that maybe we've entered a new geological epoch, just like, we have all those past layers in the rocks that we give names to, the Jurassic, the Triassic, and so forth. Well, the idea is that we've been in the Holocene epoch since the last ice age, basically, 12,000 years ago or so, and that maybe now we've entered a new epoch of Earth history characterized by a new geological force, the Anthropocene, which is the combined geological activity of human beings. And it's kind of a bothersome idea, right? I mean, it's unsettling for a number of reasons. One, maybe it's arrogant. Why should we name a geological age after ourselves? And for another, it's quite a responsibility to somehow be sort of in charge of a planet, like they say in the store. If you break that thing, you bought it. It's yours now. You have to deal with it. So it's unsettling. But I think there's also a truth to it, and the positive side of recognizing this is that maybe it's a step towards sort of taking responsibility. If we call it what it is and recognize it for what it is, then maybe that's a positive step in terms of sort of we do have to own it in that sense. So, another reason, speaking of Copernicus, another reason why the Anthropocene is kind of upsetting in terms of history of ideas, history of science, there's this narrative that the history of science has been one of moving humans away from the center of the story, of decentering humans. Something that Carl Sagan, who was a kind of a mentor of mine, he called this the great demotions. That all these discoveries we've made have moved us away from this idea that the world was created just for humans towards our being sort of peripheral. I mean, first, of course, Copernicus showed us that the Earth is not central to the universe. He thought the sun was central. Turns out that's not true either, but it was still a very big leap. And then Darwin came along and showed us that humans are really not biologically distinct from the rest of life, that we're related to all other life, so we're not special in that way. And then, of course, with the discoveries of modern cosmology and astrophysics, we've learned that not only is Earth not central, the sun is completely peripheral. Our galaxy, our cluster of galaxies is peripheral. We're really peripheral. And not only that, But the story it's such a long story. Time goes back so far that human beings have not been here for basically the whole story. We're so recent that there's no way that can all be about us. So we're peripheral and we're recent. Oh, and then in the bottom left there, it's just Darwin's insight, of course, has been dramatically confirmed by the more recent molecular biology. And, when we learn about evolution from actually studying what's inside of cells and the relationship of proteins and DNA, we understand the deep relatedness of all life. So this is disturbing, kind of, because, as Carl Sagan said in describing these great demotions, it is far better to grasp the universe the way it really is than to persist in delusions, however satisfying and reassuring. Okay, so that's why the great demotions are seen as this triumph of science. But then with the Anthropocene, are we sort of reversing this and giving ourselves a great promotion? Are we saying, hey, guess what? It is all about us. We are central. It's a little bit of a strange thing to say after being educated in how important the great demotions are. And so are we placing ourselves back in the center of the story? Well, we sort of are, and this is disturbing. But again, we can look at Carl's words. It is far better to grasp the universe the way it really is than to persist in delusions, however satisfying. And when we look at Earth and what's happening on the planet now, when we look at the data, there's a lot of data about this, about how Earth systems are changing, the composition of the atmosphere, the climate, the composition of the ocean, the land surface, the nitrogen cycle, you can go on and on. There are rapid changes in all these Earth systems due to the actions of humans. So when we add up that evidence, there's no escaping the conclusion that Earth really has entered a new chapter, and a new kind of chapter that has not experienced before. So that's the Anthropocene. And what I've done in some of my recent work is try to characterize the Anthropocene from the point of view of an astrobiologist. In other words, if we look at deep time and deep space perspective and a comparative planetology perspective on the Earth, then how do we characterize this change that's happening to Earth now? How does that help us think about our future? And how does that help us think about the possibility that similar changes may be happening on other planets? Because if there is complex life elsewhere and it does develop technology, it's possible that this kind of crisis, where a technological species will have to come to grips with themselves as a planetary force, that this might be a stage that happens to planets in a more sort of general or abstract way. So this was the subject of a book I wrote a few years ago called Earth in Human Hands, where I tried to characterize the Anthropocene basically from the point of view of astrobiology. And what I'm going to do now is just share with you a few of the ideas that are in that book. Again, for me, the starting point is comparative planetology, where we study the planets in relation to one another, and we gain insights into sort of the general rules of how planets develop. And in so doing, in studying Venus and Mars and other planets, we've learned a lot about Earth that we probably would not have learned any other way. And this slide just gives an example that I really like of comparative planetology, where you can see the similar form of a river delta on Venus on the left, Earth in the middle, and Mars on the right. And the similarity of form is obvious. And this is one thing we learned, that nature loves to repeat itself in different environments, making the same forms out of whatever the materials are at hand. So you see the basic similarity, but then when you look in more detail, you start to see differences which tell us about the different stories of these planets. For instance, Venus on the left is really, really hot. It's about 900 Fahrenheit or about 475 Celsius. So this could not have been carved by liquid water, this river delta. We know now, or we believe, that it was carved by some kind of volcanic lava running across the surface and behaving as water does on Earth because it's so hot. Over on the right, you see a dried up ancient river delta on Mars, and you know it's ancient because of the way that it's eroded and because you can see there are even some impact craters superimposed on top of it. You see that big smooth circle there. when you see impact craters on top of a surface, that helps us understand how old they are. A really young surface is very unlikely to have a large crater like that. So there are many clues that tell us, yes, Mars had liquid water like Earth, but many billions of years ago. This is a planet that has not had water for a long time, but clearly did at one point. And then in the middle, that's Earth. And when you look closely at this delta on Earth, what you see are mangrove swamps and other signs that this is a planet that is brimming with life. So we see the different stories of these planets reflected in the variations on the same theme in comparative planetology. Now I want to talk just for a minute about what we've learned, some of the big lessons we've learned from our studies of Venus and Mars, our two neighboring planets. This is the Curiosity rover just after it landed on Mars. And this picture still gives me kind of goosebumps because you can see on top of the instrument deck there, that's gravel that was stirred up in the landing. This has just landed. It's still unfolding itself. That's gravel that was stirred up in the landing and ended up on top of the rover. And this little circle, see that dark circle in the back there on the top of the deck, that round one there? That's part of an instrument that I helped design called the RAD, the Radiation Assessment Detector, which is, we wanted to measure the actual energetic radiation at the surface of Mars, which had never been done before because that's probably one of the major limits on the possibility of life on Mars. And when I see this, it's hard to describe, but when there's something that you've worked on, and of course the work starts many, many years before there's even an approved spacecraft or a launch. And then you go through a lot of trials and you go through the terror of launch, and then the even more terrifying 7 minutes of going from Mars orbit down at high speed through the atmosphere and deploying the parachutes and all this crazy stuff that has to happen. And then you finally, there's the picture and there's your instrument sitting on Mars. It's pretty intense. It's emotional. You get attached to these machines. They're kind of like our children. And we hope that they'll behave and, and stay in touch. Anyway, so what we've learned by roving on Mars, we've learned a lot, but one of the big lessons, which I'm sure you've heard, is that there used to be a lot of water on Mars. And this, on the left here, this is a river delta, another river delta on Mars. And if you look in that box with the label C there, then on the right, this is what you see up close in that box. And you can see a meandering river. So you know how rivers over time they break their banks when they flood and they meander and they change course of the river. And that's what that tells us is that this wasn't just one quick flood, that this river flowed for many, many years and many, many seasons. So this is just more evidence of that watery past on Mars. And of course now we have the Perseverance rover, which is exploring this delta in a crater that we call Jezero, and a place that we think there probably could be signs of ancient or organic evolution. And again, we find all kinds of interesting things, like this picture here shows these rounded boulders are basically river rocks. They're rounded, we believe, because they were deposited in a flood. That's how you see this on Earth in places where there's been a lot of floods and the rocks have sort of tumbled around and ended up with that round shape. And then, indeed, when we go up close to these rocks and analyze them with our instruments and figure out what minerals they're made out of and so forth, it confirms this idea that this was a watery place. So what about Venus now, turning to our other neighbor? Venus is a much harder place to explore because it's completely covered in clouds all the time, so you can't see the surface from orbit or with a telescope. And it turns out that when you try to go to the surface, as I mentioned, it's 475 degrees Celsius. The pressure there is the same as the pressure would be if you went a kilometer under the ocean on Earth. And those clouds are made out of battery acid, concentrated sulfuric acid. So it's very difficult to get a spacecraft to operate at the surface of Venus. The Soviet Union actually did it a few times. They're the only ones that have succeeded in doing that. They had these landers that lasted for about an hour on the surface of Venus. So we know much less about Venus than Mars, but what we do know again suggests probably that it had a watery past. We can see what the surface is like today. We've been able to use radar to image the surface, and we see that today it's a very volcanic surface with all this image. You can see these are all different volcanic flows and some tectonic ridges, but the surface is young. You don't see impact craters. And so when I say young in planetary terms, I mean less than 1 billion years old. So not young like you are, but young geologically. So we don't see direct signs of the past on Venus, but in the atmosphere we see clues that suggest to us that Venus did have a lot of water that's been lost and was probably much more Earth-like. What happened to the water on Venus? Well, we think that it was lost in what we call the runaway greenhouse. You know about the greenhouse effect on Earth, where you put greenhouse gases in the atmosphere, like of course CO2 or water or methane, those are greenhouse gases, and it heats up a planet. Well, Venus, probably what happened was because it was born a little closer to the sun, the oceans evaporated at some point. And when the oceans start to evaporate, then you get this powerful positive feedback. And it works like this. If the surface temperature is a little bit higher, then that evaporates more water. And you know that. If I put this glass of water out in the sun and I come back at the end of the day, there's going to be less water because of evaporation, right? When water's warm, it evaporates. But water vapor itself is a greenhouse gas. So when water vapor evaporates, that makes a stronger greenhouse, which heats up the surface some more, which causes more evaporation, which you can see how this goes. It's a positive feedback. I have Jimi Hendrix there to represent feedback, which some of you will get. I'm showing my age. I saw you left. Okay. Anyways, you can't stop it once it starts, and we think that's what happened on Venus. And the atmosphere became steam, and when it's steam, it's vulnerable to being lost to space. Ultraviolet light from the sun breaks up the oxygens from the hydrogens. The hydrogen escapes into space, and as a result, today Venus is really hot and Earth has 100,000 times as much water as Venus. Venus has almost no water, which is remarkable because we think they probably started out with the same amount. So as far as we know, that's what happened to Venus. But when I say as far as we know, the fact is we don't have a lot of really good data on this. And we're really motivated to try to understand this because not only do we just want to know because it's our neighboring planet and it's mysterious, but this is also something that can happen to a habitable planet. And this may be the long-term fate of the Earth. So we really want to understand. And in order to do that, we're trying to send some new missions to Venus. And I'm really, really psyched about this next thing to tell you about, which is that I'm on a project which has been approved by NASA called Da Vinci, and we are now building a spacecraft that we're going to be launching to Venus in June 2029, and it's designed to answer these questions about the history of the atmosphere and the nature of the surface rocks. It's basically a giant, not giant, it's only about 1 meter across, a titanium sphere that we drop into the atmosphere on a parachute. At a certain point, the parachute drops off and it's in free fall. And as it descends through the atmosphere, we're going to measure very precisely what the gases are made out of and the isotopes and a lot of other aspects of the planet that should tell us a lot more about this history and whether there was an ocean and what happened to it. And then as we get towards the surface, we're actually going to take the first ever descent photography of this mountainous area called Alpha Regio, and that should be spectacular. We're going to get stereo descent photography of the mountains of Venus on the way down. So something to look forward to in 2029. This is our team we're working with. I'm in there somewhere, and it's really a wonderful team to be working with, and this is a schematic of our spacecraft. Like I said, it's a titanium sphere 1 meter across. It has 5 scientific instruments. On the bottom there, you can see there are 2 windows. The windows are not made out of glass because glass would not survive. The windows are made out of, it's a gemstone, not diamond. No. I'm having a brain lapse. Sapphire. 10 points to the man in the front. The windows are made out of, are made out of sapphire. And that's where our cameras and spectrometers look out of. And so we're really excited about this. And by the way, there are 2 other approved spacecraft missions to Venus, all happening in the same time frame. There's a European Space Agency mission called Envision, and another NASA mission, which is an orbiter that's going to do more radar and infrared imaging of the surface. So between all these missions, we're calling this the Decade of Venus. And if you invite me back here a decade from now, I can tell you stories that will not just be, well, we think this might be what happened, but if all goes well, I think I'll be able to tell you in another decade really what did happen to Venus, which will be really exciting. But anyways, as far as we can tell, given the exploration we've done to date, comparative planetology shows us that these planets had similar origins in early environments. Venus, Earth, and Mars are very different today, but the data we're getting seems to be telling us that when they started off, they were all much more similar. It may be that the early solar system looked more like this, with all 3 planets being watery, which is really interesting from an astrobiology perspective, because as far as we can tell, it was the conditions of warm oceans on the early Earth and the right energy sources and organic molecules that allowed the origin of life to happen about 4 billion years ago. And at that same time, we believe Venus and Mars may have had those same conditions. So that's pretty exciting. And it may be what we're learning is that rocky worlds in the universe start out with the right conditions for the origin of life. And the really rare thing about Earth may not be so much starting out with those conditions, but maintaining the conditions to perpetuate life for all these billions of years. And Venus and Mars were not so lucky, at least from the standpoint of our kind of life. All 3 of these planets changed radically from those early days. They all went through some sort of catastrophic change. In the case of Venus, there was a runaway greenhouse, and Venus today is a desiccated oven of a planet. In the case of Mars, Mars was too small to hang onto its atmosphere. It doesn't have enough gravitational pull, and all kinds of forces have allowed that atmosphere and the water to escape. And Mars today is a dried out, frozen desert. And Earth also went through a radical transformation. What happened to Earth was Earth came to life. And we've been learning more and more that the character of Earth has been utterly transformed due to life, that Earth, in a sense, really is a living planet. Obviously, the atmosphere, the oxygen we breathe is created by life, but also we've learned more and more that the composition of the oceans and even the rocks themselves, 3/4 of the minerals on Earth wouldn't be here if it wasn't for the influence of life. So Earth is thoroughly transformed by life, and this relates a little bit to a theory you may have heard of called the Gaia hypothesis. This is James Lovelock and Lynn Margulis, a chemist and a biologist who in the 1970s proposed, and this was their paper, atmospheric homeostasis by and for the biosphere, the Gaia hypothesis. And it made quite a splash because basically, well, they pointed out that starting down here, that the atmosphere of Earth is utterly different from the way it would be if it was lifeless. That on Venus and Mars, the atmosphere is all carbon dioxide. That on a dead Earth, the atmosphere would be all carbon dioxide. But on the living Earth, you have all this nitrogen, oxygen, and very little carbon dioxide. That's sort of the most dramatic example, but they enumerated all these other ways in which the Earth has not only been transformed by life, but they went further and said that in a sense, Earth is being regulated by life. That the cyclic activity, the biogeochemical cycles, and the bio in there is very important. The biogeochemical cycles of Earth act over the long term to modulate the climate and to modulate other atmospheric characteristics. So it may be that the reason why Earth has stayed such a fit planet for life all those billions of years, while the neighboring planets have not, apparently, is because the presence of life itself has helped to maintain that homeostasis. It's still a sort of controversial idea, but it's also been very fruitful in developing what we now call Earth system science, which is sort of Earth science where you incorporate biology into understanding the cycles and the behavior of the planet. As my colleague Colin Goldblatt put it at a meeting I was at recently, the defining characteristic of Earth is planetary-scale life. Earth teaches us that habitability and inhabitants are inseparable, which is important if it's true in looking for life elsewhere, because then we tend to think of we're trying to find a planet with habitable conditions. It has to have the right temperature, it has to be the right distance from a star, it has to have the right chemical mix and so forth. But it may be that life is not something that just exists on a planet with the right conditions. It might be that life is something that happens to a planet and helps ensure those right conditions. So we're still trying to tease out the extent to which that may be true as a general principle, but this idea of planets as living worlds is a very important one to try to understand when we think of the possible characteristics of other worlds with life that we may find in the universe. So life happened on Earth, and then it sort of took over the planet and became a planetary property, if you will. Now, more recently, Earth has come under the influence of a new type of geological force, the global activities of humanity, which, as I mentioned, defines the Anthropocene. And a question that I'm fascinated by is there a sense in which intelligence like life could become a planetary property? In other words, a property that's integrated in some sort of robust, stable way in the functioning of a planet over the long term. Hold that thought, but I want to take a slight detour here, because what I want to do now is try to sort of characterize what the Anthropocene and human influence is from the planet's point of view. What kind of a change is the Anthropocene? How do we characterize it in terms of the different kinds of changes that have happened in planetary history? And in so doing, I think it's important to remind ourselves that we are not the first species to come along and radically change the planet. In fact, we're not the first species to come along and cause a mass extinction of other species. In fact, we're not the first to come along and, in the search of exploiting a new energy source, pollute the atmosphere in a way that wipes out other species. That's been done before. This slide shows these little guys are cyanobacteria. And they look innocent, don't they? But 2.5 billion years ago, these cyanobacteria discovered a new energy source, and they were so effective at exploiting it that they polluted the atmosphere with this poisonous gas, and they wiped out much of the life that existed on Earth, well, closer to 2 billion years ago. The energy source they discovered was solar energy. They were the first to really mass produce with photosynthesis, and that poisonous gas that they released was oxygen. They oxygenated the atmosphere, and oxygen was completely poison to life at that time. Oxygen burns organic matter. That's why you can burn a log in your fireplace. Now, of course, we love oxygen. You know, I certainly do. Good stuff. Good oxygen you got here in Krakow. The thing about life is it's very opportunistic. And when oxygen first appeared, it was reacting with other organic molecules and destroying life. And then some form of life came along that could exploit that reaction. And it's very powerful when harnessed, and that's called respiration. That's what we do. Every cell in your body has these little factories, basically, that burn oxygen in a controlled way and store energy, and you use it. That's how we power ourselves. So what was a catastrophe then became an opportunity for life to have more energy than at its disposal than ever before. Okay, so that's a little parable about the cyanobacteria, but then we look at ourselves now, exploiting an energy source, polluting the atmosphere, threatening extinction of other species, and we shouldn't feel very good about it. You look at the cyanobacteria and you say, well, they're innocent enough, they're just bacteria, right? But we're not innocent because we, at least to some degree, understand what we're doing. So when we talk about this and we say, well, so what's really the difference between us and the cyanobacteria? One way you can look at the changes happening now is that we are the first geological force to be aware of its own existence. This is my favorite way of thinking about the Anthropocene. That's really what's new here, is the awareness factor. And that creates potential for course corrections, but also great peril, because we have powers at our disposal that we clearly do not have fully at our own command. So now I want to tell you about what I call the 4 kinds of planetary change. In an effort to characterize this new sort of change that's happening to the Earth, I've looked at all the major kinds of catastrophic changes that happen on planets, and I decided that, in a sense, I think there are 4 kinds of planetary change characterized with respect to the role of life in them, okay? So when I talk about planetary changes of the first kind, these are random catastrophes. So this is just, these are catastrophic events that life has nothing to do with. Life is not implicated. Life is an innocent bystander. Random things. An asteroid hits your planet and wipes out the dinosaurs, or wipes out most of the species on the planet. That's, what could be more random than that? But also in this category, many mass extinctions have happened because some change in the interior of the Earth leads to some sudden burst of volcanic activity, which changes the climate and leads to a mass extinction. This has happened several times. So these are, just sort of, this is when bad things happen to good planets. You're in the wrong place at the wrong time. That's what I mean by random catastrophes. Planetary changes of the second kind are what I call biological catastrophes. When one species or one kind of life is so successful at doing what it does to survive that it propagates around the planet and changes the environment in some way that is disastrous for other species. And I symbolize this with the green leaf because I already mentioned the oxygen catastrophe that happened when when life evolved photosynthesis. There were other examples. This is the best example. So that's what I mean by biological catastrophes. Now, when I get to the next 2 kinds of planetary change, 3 and 4, they both involve cognitive processes. This is where cognitive processes enter into planetary change. But there's a very important distinction between the changes of the 3rd kind and changes of the 4th kind. When I talk about planetary changes of the 3rd kind, this is what I call inadvertent catastrophe. And here you have one species that's gotten so good at local survival, solving local survival problems, and using technology to alter its local environment in ways that make it very successful at surviving. And in fact, it becomes so good at solving these local survival problems with its technology that it spreads around the globe, and completely unbeknownst to themselves, they are changing the planet. So this is inadvertent when you are causing some global catastrophe, but at least at first have no idea you were doing so. And I symbolize this here with traffic because it illustrates one aspect of this, which is the aspect of agency. Here we have some creatures that are very good at surviving a local problem, are very good at solving a local problem, which is, in this case, how do you get from Oakland to Alameda during rush hour? And they're doing fine. Driving traffic actually works really well if you think about it. The accidents are really rather few and far between. We're good at driving. People have agency. Without even thinking about it, you step on the brakes, you steer. It works pretty well. But that's the agency on the level of the individual drivers. If you look at the whole system, you can ask, well, who's driving the global transportation system? And the answer is really nobody. Nobody's driving it. So it's an example of where we're sort of participating in this system, but nobody's in control of it, right? And that leads to what I call the Anthropocene dilemma. It's dangerous and unstable when the scale of your action exceeds the scale of your awareness. You can think of a child who has not yet developed situational awareness in this regard. You know, think of the image I have is like a kid with a big backpack on, and they walk into a store, and they turn around because they get excited by something, and they knock over a whole rack of candy with that backpack. You know, you say that kid doesn't have situational awareness. When the scale of your actions exceeds the scale of your awareness, it's unstable. And in a sense, that's true of a lot of human activities right now, and that's what I mean by inadvertent catastrophe. And some obvious examples of that, you know, the most obvious and pressing example, of course, is the great rise in carbon dioxide. This slide's a few years old. It's now over 400 ppm. And we know a lot about this, and I'm not going to go into detail here because you're well aware of the dangers of rising carbon dioxide and the disappearance of the sea ice and all these consequences that we are rightfully very concerned about. Another example of inadvertent change was the destruction of the ozone layer, where we developed these chemicals that seemed safe and harmless for refrigeration. In fact, they are safe and harmless down here in the troposphere where we live. But it's a classic example of unintended consequences, because when some of those CFCs, those chlorofluorocarbons, leak up into the stratosphere, then they do something nobody had anticipated, because the chlorines get split off by ultraviolet light, and when you have chlorine atoms, it destroys ozone, and that was a big problem. By the way, part of the way we discovered that we were destroying the ozone layer came about because we were exploring the planet Venus, something most people don't know. There's a mystery about Venus, which is, why isn't there more oxygen in the upper atmosphere? Because it's mostly CO2. The CO2 is being split up by ultraviolet light into carbon and oxygen. You should see more oxygen in the upper atmosphere of Venus. It's not there. Some scientists figured out it's not there probably because there's a little bit of chlorine in the upper atmosphere of Venus, which eats some oxygen compounds. Some other scientists read that paper about Venus and said, oh, wait a minute, what about all that chlorine we're starting to put in Earth's stratosphere? Uh-oh. And that helped them realize. We would have realized it eventually, but it helped them see what was going on. So it's a good example of how this curiosity-driven research can sometimes lead us to some very important survival lessons. At any rate, what happened here was the ozone hole was discovered. It started to deepen in the 1980s, and then it really started to deepen, and people got spooked by it. And there was a big argument about ozone. It was a lot like the arguments about climate change, about carbon that we've had more recently, where some companies said, oh, it's a hoax, that's not really happening. And they said, oh, you know, it's, you're just trying to scare people, and they denied it because they were making money off of the CFCs and all that. But then it became very obvious that the ozone hole was real, and even the companies that were making the CFCs, they got on board with saying, yeah, we need to do something about this. Now, granted, before they did that, they patented the replacement chemicals that would be needed, so there was some enlightened self-interest here. But nonetheless, the world got on board and made an agreement, the Montreal Protocol, which has worked. It is working. It takes about 50 years to repair the ozone hole, but it's on track to being fixed. So I use this as an example of the third kind of planetary change, inadvertent, but it's also my first example of what I call planetary changes of the fourth kind, which is intentional. Because here's a situation where we saw a global problem, and on a global level had a conversation about it, made an agreement, and were able to do something about it. So I consider this a very hopeful example. It doesn't mean it's going to be easy to solve global problems. In fact, there are a lot of ways in which the carbon problem is a much more difficult situation than this. It's much bigger, there are much bigger economic stakes, for one thing. But at least it's proof of concept that this kind of thing has been done before, right? That we've recognized a danger to the planet, and as a planet come together and said, let's do something about it. Now, what about other examples? Well, of course, in the upper right here is the most pressing one I've already mentioned, and that is the need to, as rapidly as we can, change the energy sources we're using to power our global civilization into ones that are not wrecking the natural systems that we depend upon to survive. The good news is that this change is underway. The bad news is it's happening way too slowly. I mean, there is some good news. The cost of alternative energy has gone down much faster than anybody predicted. And you can argue that we're in the process of making this necessary transition, although you can also persuasively argue that we're taking way too long. I look at it like, I think in 100 years, we will be completely off fossil fuels. We'll look back on this time and think about them the way we think about hunting whales now, using whale oil for power. And we'll think, it was really dumb that we did that for so long, because look at the damage we did. But it's good that we got off it for the most part, and we're not completely off of whales, and we won't be completely off of carbon, but there's still whales in the world, and there will be damage, but I don't believe that we're doomed. We can get back to that if you want. But so that's an intentional change, a planetary change of the fourth kind. Now, going out to longer time scales, on the lower left here, we have the possibility of defending against asteroid impacts. Just as the dinosaurs were wiped out 65 million years ago, there are a lot of objects still out there in the solar system, and eventually, it's not a question of if, it's a question of when a threatening one will be heading towards Earth. But unlike the dinosaurs, we have a space program, and there's absolutely no reason why we couldn't change the orbit just by a few minutes, give it a little push, and it would pass harmlessly beyond the Earth. So this is a way in which ultimately I think, we can pay back the biosphere for some of the harm we're doing now, and maybe in the long run prevent the next mass extinction. And going out into even longer time scales, this is a picture of an artist's conception, obviously, of the last ice age, and there will be other dangerous natural climate changes if we wait long enough. We have this illusion that left to its own devices, the Earth is this perfect Eden, and if we just leave it alone, it will be a great place to live forever. But that's an illusion, because our whole civilization has sprung up in this unusual 10,000 year time of relatively stable, relatively warm climate, which is an anomaly in Earth history. And if you wait long enough, there will be another ice age. Our civilization would not survive. Billions of people would die with our current population. But we have tens of thousands of years before we have to worry about that. So I'm not particularly worried about that. These are just examples of how, if we're going to start thinking of ourselves as a geological process, then we could start thinking also on geological timescales. And in the long run, I believe if you can anticipate a problem, then you could do something about it, then you have an obligation, a responsibility to do something about it. So these are examples of, in the long run, all in the same category of intentional planetary change. Now, thinking about these four kinds of change in a different way, what if we think of the rest of the universe and planets out there, and they say the exoplanets? Where would you find these different categories of change? Well, category one, the natural disasters, the random events, that'll happen on all planets. At least any planet that's good for life, because any place with geological activity and an atmosphere, which are the characteristics we think planets ought to have at least life like ours, will have natural disasters. They'll have earthquakes, volcanoes, floods, hurricanes. That's the nature of planets. So that kind of disaster will happen everywhere. In terms of biologically induced catastrophes, I also think that will happen on all planets with life. Because, we can talk about what is life, and that's a really interesting question, which I've skirted so far, and which astrobiologists have to think about a lot. But whatever it is, it seems like it's probably something that multiplies and alters its environment. And with those characteristics, then you could see how environmental changes will happen occasionally that are to the detriment of other species. Now, what about categories 3 and 4, the cognitive changes, the inadvertent and intentional changes? Of course, we don't know, but asking the question is another way of framing the question, are we alone, which is sort of the central question of astrobiology. Is this a common story, including the possibility of intentional changes? This sort of crisis, this Anthropocene crisis which we're having of how do we deal with the fact that we're planet changers, is that an evolutionary turning point for other planets that develop complex life and maybe even technology? This leads us to something that astrobiologists call the Fermi paradox, which is named after the Italian-American physicist Enrico Fermi, who was a very important 20th century physicist. And he framed this question, where are they? I mean, he didn't make up the question, but he framed it in terms of the physics. If you have a galaxy and you have life here and life here and life here, and occasionally that life develops intelligent civilizations, and you look at the time scales they should take to travel across the whole galaxy, then they should be here already. So where are they? That's what he means by the paradox. If life is probable and intelligence is possible, then why haven't we seen obvious signs of advanced aliens? And people have discussed this, there's books and books about this, but some of the possible answers are, well, maybe there isn't any, maybe there is something we don't understand that's completely unique to Earth, and we are completely alone, that's possible. Maybe we just haven't looked in the right way, or looked long enough. Maybe we just don't understand how to recognize alien life and that the signs are right in front of our faces. Maybe in some ways they're hiding from us, or they think it's not a good idea for us to know about them. These are all answers that have been proposed. But built into a lot of these discussions about the Fermi paradox is a kind of assumption about the nature of civilizations. The assumption that, quote, advanced civilization means endless expansion and exponential increase in energy use. That you look at human history, and that's our history, and people think, okay, so a really, quote, advanced civilization will be obvious because they'll be using so much energy and wasting so much energy, and they'll expand throughout the whole universe, so they'll be easy to find. But it's interesting to think about whether that's the best way to think about the future of our civilization and maybe the long-term paths of other civilizations. And recently, there was a paper by some friends of mine they called it the sustainability solution to the Fermi paradox. The idea that we are learning that longevity on Earth will require recognizing limits and integrating ourselves gracefully into the functioning of the planet. Not just continuing to build and change everything, but learning how to work with the planet. And maybe that challenge we're facing now is representative of a kind of evolutionary transition that can happen on other planets. And maybe the nature of long-lived societies then could be to develop a kind of ethic of sustainability. And so maybe it's not in the nature of long-lived civilizations to expand relentlessly, and so then maybe the signs of other civilizations would be more subtle than what we've been looking for. So it seems, though, that maybe the essential problem determining whether our intelligence is to be long-lived or more transient is our struggle to achieve some kind of global intentionality. And in this light, I've asked, is it useful to think of defining intelligence as a global property? And I wrote about this a little bit in Earth in Human Hands, and I'm just going to skirt lightly here because I want to finish up soon, so we have, I'll get a few more minutes, and then we have time for discussion. But in Earth in Human Hands, I defined planetary intelligence as globally coordinated cognitive activity that can result in more stabilizing behavior. Stabilizing because if the action of technology includes an awareness of the global effects of that technology, and that feedback loop is incorporated into the deployment, then it's naturally a negative feedback, and it's more stable than a positive feedback like it described with the runaway greenhouse on Venus. And by the way, such a definition leaves it undetermined whether intelligent life has arrived on Earth. And I'm not sure it has. So this is not, in that sense, a self-aggrandizing definition. It's something that we can aspire towards and imagine might be happening on some planets. So what do we even mean by intelligence, and how would it possibly make sense to think of it on a global scale? We usually think of intelligence as a property of individuals. Some creatures have it, some creatures have less of it. inanimate objects probably don't have much of it. But it can also be a property of collectives. You see this in the social insects, where a hive has the ability to make decisions through collective behavior that one particular insect doesn't have. And for that matter, you see it in the human brain. We heard this great talk last night about brains, and an individual neuron is not an intelligent creature, but somehow the collective action of all those neurons is some emergent intelligence. People have even talked about this in forests with the underground networks of fungi communicating between trees when there's a threat and so forth. So this idea of collective intelligence is kind of out there in the literature in various ways. And it makes me wonder, is it possible that we've been sort of constructing in our technosphere something with cognitive properties in which we're perhaps unaware? You think of all these global networks of human activities, trade. I mean, the internet is an obvious one. People have talked about, well, maybe the internet, we're sort of making this big brain. And maybe we are, but I think it's more broad than that. You think of the networks of trade and transport and economy, governance, information, even conflicts are forms of connectivity. And there are ways in which you can see it as forming sort of a primitive cognitive neurological system, in the sense that you have signals between all these different parts which are responding to external circumstances and altering their behavior in certain ways. There's an idea it came out of thinking about artificial intelligence and trying to understand the human brain, and this guy Marvin Minsky at MIT, who was a artificial intelligence pioneer, he wrote this really interesting book called The Society of Mind, where he said maybe the nature of a human mind is not this so much a coherent whole as lots and lots of little individual agents that are interacting in various ways and forming this collective emergent property of intelligence. He said, we'll show you that you can build a mind from many little parts, each mindless by itself. And in Minsky's view, the mind was a community of agents, what he called agents, each with limited powers that can communicate only with certain others. But the powers of mind emerged from the interactions between these agents, none of which in itself had significant intelligence. So in thinking about this sort of global property, in my mind, I turned the society of mind around and started thinking about the mind of society. What if you turned it around and you think about all these networks of connections? Is there a way in which we can look at this as some kind of cognitive activity? Now, granted, you might say, if it is, it's mentally ill, or it's pretty dumb or pretty immature, looking at the ways in which our global interactions are or are not leading to collective action. I mean, think about the pandemic. I think nobody here would say, oh, the world responded perfectly to the pandemic. Aren't we proud of ourselves? But on the other hand, I think we can say the world did respond to the pandemic. There were global conversations and global arguments and global distributions of various research and knowledge and vaccines and so forth. So in a very imperfect way, you can look at that as a crisis that was met cognitively by the globe as a whole. And there are obviously lots of other examples. I want to finish up, though, because I really want to get to conversation. So the last thing, or almost the last thing I'll say about this, is that this idea of planetary intelligence, with a couple of colleagues, I've developed it a lot further than I have time to share with you tonight. But if you're intrigued, we have 2 publications on this. This one on the left, Intelligence as a Planetary-Scale Process, was published last year in the International Journal of Astrobiology. It's an open access publication. Anybody can read it for free online. I was going to put the link, but actually it's so easy to find. If you just Google me and the topic in International Journal of Astrobiology, it'll pop right up. And we go into a little bit more detail on some of what this might mean in a slightly more scientific way in terms of theories of emergence and complex adaptive systems and information theory. I invite you to check it out if you're intrigued. And then we also wrote an article down here on the lower right called Is Earth Smart in a magazine called The Atlantic. And that's a more sort of less nerdy, more, I wouldn't call it popular level. It's, an erudite publication, but it's not written in the arcane language of science. So if you're interested, and that's also open access online. So if you're interested, you might check out those publications, and it goes into more detail. But we define planetary intelligence as the acquisition and application of collective cognitive function operating at a planetary scale and integrated into the function of coupled planetary systems. In other words, feeding back into running the planet in the long run, that sensing, that knowledge of the planet into how you deploy your technology. That is how ultimately you would display planetary intelligence. Is there such a thing? Well, and then again, I don't really have time to get into this, but in that paper we talk about this in terms of information theory and network theory and all these nerdy terms that I've listed here, which again, I urge you to check it out if you want to know more about what we've written about this. But basically, why ask this? What is it good for? And I'll say, I think it might prove useful for at least three different domains. One is just to understand Earth systems and possible exoplanets. If intelligent networks can become part of the way a planet functions, and one thing I haven't said is that this may not depend even on humans and technology. There are ways to look at even the bacterial interactions globally as a kind of cognitive system, because there are a lot of biological feedbacks that predate the deployment of technology. So in that sense, this analysis may not even require a supposedly intelligent civilization using technology. It certainly, I think, is applicable to this question of trying to understand the Anthropocene, and that's the way I've framed it this evening. And also, in terms of what we call technosignatures, which is trying to find the signatures of technology being deployed elsewhere. In SETI, the search for extraterrestrial intelligence, we've been listening for radio signals for 50 years or so now. Haven't heard any yet. We're still listening. Maybe we just haven't listened in the right way to the right star. But there's this movement now to think in a more broad way about technosignatures. Like, how would we find a civilization that's not sending signals? Now that we can observe exoplanets, what would the observable properties of a planet with life and civilization be? And maybe that's relevant, this idea of planetary intelligence, because I think that if a civilization is going to last for another, we've been here for 10,000 years. If we're going to last for another 10,000 years, it will be because we've developed this ability to incorporate our knowledge of the planet into the way that we basically run our civilization. And I think you can argue, and I have argued it, that would be a general property of long-lived civilizations. And so this gives us a framework for thinking about what those signatures of civilizations that last for a while might be. We can even think of this, and I really am finishing up now, but we can even think of this in terms of, we're starting to be able to observe exoplanets and what's in their atmospheres. And we can certainly differentiate between different kinds of biospheres. A more mature biosphere like Earth's, for instance, might have a lot of oxygen, whereas a primitive, what we call an immature biosphere, might not, for reasons I've briefly mentioned. Similarly, what we have today, you could call an immature technosphere. We have all this CO2 and other pollutants we're putting in the atmosphere, and I would argue that that's not going to be the quality of a mature technosphere, but it might have other observable spectral signatures. So this is not something that we've developed very well. It's an idea that we've just kind of thrown out there, but I think that it's possible there are observable consequences. I'll finish up by showing you a cartoon that my friend John Lomberg drew, whereas if we get this wrong, then this is the nature of the habitable zone. Venus was too hot, Mars was too cold, and Earth was too dumb. But personally, I'm an optimist. I don't believe that. But I do believe that if we're going to create what I call Terra Sapiens, which is this vision of a wise Earth where we fully incorporated our knowledge of Earth systems into the way we behave globally, then we do need to become a new kind of entity on this planet. And we need to learn to live comfortably over the long haul with world-changing technology. And one of the keys to this, I think, is the widespread propagation of a worldview that is global and, very importantly, is multi-generational, long-term worldview. And so finally, I'm just going to end with a quote from one of my heroes, Dr. Martin Luther King, who said, "If we are to have peace on earth," which I also interpret to mean if we are to create a truly sustainable global civilization, "our loyalties must become ecumenical rather than sectional, must transcend our race, our tribe, our class, and our nation, and this means we must develop a world perspective." And with that, I'm going to stop. Thank you. I'd be happy to entertain questions.
Thank you. Thank you very much. I think that we will have a very brief question section, but I think it wouldn't be fair if we hadn't allowed, I guess, at least one brief question with a brief answer, and then we will see what's available because we want to do our business. Maybe also we will, feed you to those people to talk to you and fight you individually. But let me see. Is there anyone who would like to ask something quickly? Should I come with a microphone? Well, maybe I will. Let's see now. I've seen a hand over here. Yes, you're the lucky one. Thank you. Please be brief.
Yeah, sure. Hi, my name is Adrian, and I'm sorry for my English. I didn't speak it very well for like a couple of years, so let me give you a brief question. So I've learned that the Voyager probe found that there is a life on Enceladus, one of the moons. So how do you feel about that? What do you think about that? What are your thoughts? Do you think that there is a life, and should we go there, and should we explore the Enceladus moon a little bit further, because it's like the first ever occasion to discover and to explore extraterrestrial life?
Yeah, it's a good question, and your English is much better than my Polish, so don't feel self-conscious at all. Yeah, Enceladus is he mentioned Enceladus, which is a moon of Saturn, which is probably one of the best places to look for life in our solar system. You mentioned Voyager. Well, Voyager was a spacecraft that first flew through the Saturn system and noticed that there was something strange about Enceladus, that it's very, very bright. But then we had another spacecraft called Cassini that went into orbit around Saturn, and Cassini discovered that there's something really strange about Enceladus, which is that it's out of its south pole, it's blowing water into space constantly, and the south pole is very hot. So there's a hot spot there, and it's got a geyser that's shooting water into space. So apparently inside of Enceladus, there's a liquid water ocean, and by studying what's in that geyser, we've learned that there's organic molecules in that ocean, even better. So as far as we know, I mean, what do you need for life? As far as we know, it's liquid water, organics, and energy. Now, we might be completely wrong, but that's what we think. And all three of those qualities are met in Enceladus. So the answer is yes, we should explore there. It's one of the best places to go to look for life. And by the way, one thing that's neat about Enceladus is that because that geyser is shooting out of the interior, you could sample the interior just by flying through that geyser and seeing what's in it, or even go to the surface and scoop up some snow and see what's in that snow. So you can sample the interior of Enceladus pretty easily without actually having to dig inside. So yes, it's definitely something that we will be doing in the future.
Thank you very much. Thank you. Unfortunately, I think we really have to finish, so feel free to stalk our guests. And also, we'll have a chance to talk even more during the next meeting. So thank you very much. Thank you. And in about 15 minutes, we will have a talk over here also about life in the cosmic scheme. So stay tuned. Thank you very much.